about, I think, my last remaining liquid crystal project. So this is a project that is a collaboration with Doug Cleaver, and all of the results I'm going to show were done by his student, Alireza Dastan, who has recently graduated and has a postdoc in Iran. So what I'm going to be telling you about is the emergence of chirality in achiral systems. So we've heard tons and tons and tons about liquid crystals and chiral liquid crystals, but usually when we're talking about chiral liquid crystals, as Raphael said this morning, it's because you add in a chiral dopant. But what I'd like to talk about is what happens when you don't. So so I guess chirality is pretty much ubiquitous in the biologic world. So this is a very hierarchical bundle of bundles of collagen, hand drawn by Yves Boulegon. So this is one of my favorite illustrations from all of physics literature. And so here are some beetles. Oops. No, I'm not going to restart my computer right now. Okay. So the idea is that if you shine left circularly polarized light, you see reflectance, and if you shine right circularly polarized light, it absorbs. And it turns out that there's a cholesteric pattern in the cuticle of the beetle, and this is similar to some of the plywood textures we heard about earlier in this conference. Okay, so the optical properties of a lot of things in nature are governed by their microstructure. So as we saw with the beetles, there is a helical chiral microstructure in their cuticles, and then we also see this in these berries, and they have this beautiful iridescence to them. And it turns out that this happens just before they're ripe and ready to be eaten. So when they're not ripe, they're sort of dull, normal, berry-colored. And right when they're ready to be picked or eaten by bugs, they turn this beautiful iridescence. So probably this is signaling that bugs or birds should eat them and disseminate their seeds. Okay, so I'm going to talk a bit about chirality in liquid crystals. So we've seen the Frank free energy probably 20 times so far in this talk. I guess the only term that is relatively important to this for me is the twist term. So this K2 term is telling us that there is a preference for chirality. And in liquid crystals, I guess I will also point out the smectic free energy. And I'm going to point this out for a reason that the only term that remains from the cholesteric free energy, from the Frank free energy, is the splay term. Every other term is not going to be present because there's, so if you want to write down something as a director field, so this is a normal, and the normal of the surface is proportional to the gradient of some phase field, and we know that the curl of the gradient has to be 0. So basically, there's an incompatibility between having layered structures and having chirality. So what I'm going to talk about a lot today are discotics. So this is one type of liquid crystal that we haven't seen here, but there is a lovely poster outside on DSCG. So there's a lot of different kinds of discotics, primarily sunset yellow and DSCG are the two most common, and they basically have a bunch of aromatic groups in a plane, and they like to stack one on top of each other. Then they form these stacks, and these stacks have nematic order. But one thing about these Discotics is that the K2 term, the twist elastic constant, is much, much, much lower than it is in standard standard nematogens like 5CB and things like that. So these have quite a high propensity to twist. So if you imagine putting them in a capillary tube with homeotropic anchoring, normal nematics will just have this escape in the third dimension texture as their way to accommodate these boundary conditions. But when you've got a structure that has a very, very low twist constant, what you're going to find is that instead of having this escape texture, you're going to have a twisted escape texture like this. So you're getting sort of rotation from the outside towards the center. So I guess I have, this is not the appropriate picture. So these are both planar alignment on this side. But so these are planar aligned. This is homeotropic. You see them in both. They're both, you've got one is a twisted escape, and the other basically you also end up with a twisted escape texture. Mm-hmm. Okay, so this is an experimental image, and you see that you form instead of an escape pattern like I showed you in the beginning. What you do is you find two plus a half disclinations, and they wind around each other in helices, and you find that there are quite large domains that are homochiral, and then you see these defects right here where you have two homochiral regions coming together and the helices can't continue through. Okay, so there are sort of two ways of thinking about sort of self-assembly and elasticity, and I think we've heard different bits about each of them. So there's this idea from the molecular scale that you've got some puzzle pieces and they fit together in a certain way. You have nucleation and growth, and everything is sort of emergent from these local roles. And then on the other hand, a lot of us are continuum mechanists. So we like to say, okay, well, we've got some effective theory. I'm going to write down a field theory for it. And I have some elasticity, and all of my structures emerge from this elasticity. Okay. So, the system I'm going to talk about kind of has to blend these two ways of thinking. So what we find is that the local ordering of things determines the elasticity, which determines the pattern. So it's this sort of back and forth between local order and elasticity that's going to govern the final shape. So this is a little example of the system, or one of the two systems I'm going to talk about. So these are just Discotic particles. They're ellipsoids. These are molecular dynamic simulations, and they have a sticky face-face interaction. So these are mimicking the Discotics that we've seen before. So what you see is that this is the start of bundle formation here. So you're seeing structures, these disks adding to the end of the bundle, and at some point, so they're fluctuating around, and at some point they all together gain a chirality. So you're starting to see these guys twist. And just to guide your eye, the way these are colored is these are colored by their normal. So the normal to the layer that goes to a point on the unit sphere, and that determines the coloring. So when you see these sort of soft gradients of color, so it's going from yellow to lime green or something like that, that's telling you that there's a twist, that they're almost pointed in the same direction, but there's sort of this overall rotation. And you can see as the bulk rotates, it's gonna go from green here, maybe back to blue as it tilts up further, or red when it's to the side, something like that. So that's going to be how almost every image is colored in this talk. Okay, so this is formation of one helical bundle. Okay, so the idea is that this process involves quite a few steps in order to get to this final chiral state. So the size of this little configuration is going to determine what its ground state is going to be. So if I have just one disk, there's only one thing it can do. It can point in some direction. When I have two, there's again no chirality. They're just stuck on top of each other. So they form these little threads, aggregates that have maybe 4 or 5 threads to them, and they're straight. There's nothing else they can do. They can just stack on top of each other one by one. When two of these stacks come together, they're going to interdigitate, and there's again no chirality. So there's just a symmetry in between them. But when you've got 3, then it wants to interdigitate with both the first bundle and the second bundle. And it can't do that because there's a shift in registry. So what happens is everything sort of reorients and tilts over, so you can have these chiral structures like this. So you need this, this structure in order for the whole bundle to grow. So before that, everything will assemble and fall apart and assemble and fall apart, and you need a seed like this to form in order for the entire system to grow. Okay, so what this is showing, this is a histogram that shows the probability of finding a bundle in the entire simulation box with this many threads in it, and the color is telling you what the probability is. And what you find is that there are these stripes here of more and more probable numbers, and these correspond to completing rings around the central cell. So at first you have 7, and then you add another 6 to it, and then you add another 6 to it, and so those are these stripes here. So it's more common to find these completed rings than it is not. Okay, so this is, you can scale all of these things. You can tune both the face-to-face interaction, and you can tune the aspect ratio of the oblate ellipsoids. And the idea here is that depending on how these things change, you can go from having a straight configuration, so this is very weak face-to-face interactions, and a very fairly oblate ellipsoid, to having, I guess, low face-face interactions and very thin ellipsoids is going to start becoming chiral, and you get sort of more and more chiral as you go on. So it turns out that when you make these things, if you just keep adding more and more particles into it, eventually you completely untwist. So you twist for quite a while, that's the lowest state, and then once you have too many of them, you globally untwist. The entire aggregate rearranges. And this has to do with, so this is part of a paper by Greg Grayson. So they're talking about the stress at the edges of the edges of these bundles as the particles grow and grow. Yes? Yeah, so this is a numerical observation. So there's sort of two paths to this untwisting. And so the reason that these untwist is that the twisted bundles, you have you have a high stress at the edge, so it's going to want to realign. So once that gets too big, the entire configuration untwists. So you could either use that to set a length scale, which is common, but if you just keep shoving in more particles and let it do what it wants to do, it will eventually untwist. It cannot do that because they're interdigitated with one another, so that so this overlap means that if there is twist present anywhere, it's going to have to propagate out. So you can't have, you would just end up with separate structures. Yes? Yeah, absolutely. So you can't, you do get either break up, I mean, if there's something that sets this size, they could break up into different groups, but it's unlikely that you'll have a core that's chiral and a straight exterior. So those are the... Absolutely. So the way these simulations are done is that they wait until you get a chunk that nucleates. They do a whole bunch of simulations and wait for those to nucleate, and then they take the ones that nucleate with one chunk and run those, and if they nucleate multiple chunks, they throw those away. So if you did have multiple chunks, you could have, you know, a left-handed one and a right-handed one. They could interact in different ways, but just sort of for computational ease, they decided to look just at one. So there's not really any information about their interaction right now. There is for a couple of other ones I'll show you later. So the other system that we're going to look at are Discotic amphiphiles. So we've added a solvophilic region to the edge of each of the oblate ellipsoids, and these are going to, there's some spherical particles that are a solvent. So we're only showing things here that are part of bundles. Everything else is not colored, but they are in a sea of disks and spheres. So what you're seeing here is the formation of this little cluster that's going to eventually form the microstructure. So what you're seeing is I guess right now there's about 4 or 5 threads, and it's fluctuating around quite a lot. And at some point, it's going to, I think I have to fast forward a little bit. So at some point here, we've got about 6 threads. And at 6 threads, this is just about enough for it to develop some chirality. So early on, you're getting these sort of parallel fluctuations back and forth. And once it gets wide enough, you're going to start seeing some twist to it. So you can see these gradients of color starting to move across it. And these are going to continue to grow laterally. So we've got about 7 now. This is for about 12 of these threads. And you can see that it's clearly starting to form a bit of a helicoid. And then this is what it looks like at the end of the simulation. We're not. So these are achiral systems, and the idea is that depending on the size of the aggregate, the lowest preferential conformational free energy is going to have chirality to it. Yeah, that's a great question. So the bilayers, the leaflets of ellipsoids, those are pretty solid. They can hop around a little bit, but not very much. The layer of spheres inside, the lubricating layer, is a fluid, and you can look at the particles diffuse through, and they exchange freely with the solution. So these you can truly think of as a liquid, and then everything else you want to think of as sort of a solid. Okay, so using just this system, what we're going to do is we're going to change the hotspot size, and the number here is the percent of the circumference of the oblate disk that is solvophilic. So 50% means half of the disk-like spheres. And then the other thing we're going to change is the aspect ratio of the disks. So they are always unit radius in the round direction, and then this is the height of them. So, okay, so when we have very fat ellipsoids, and they don't have a lot of area that wants to contact solvent, they're pretty much flat. If we shrink them a little bit, what we find is that they get these nice helicoidal structures. Shrink them even more, we can get orthogonally arranged, again, flat bilayers, but if you grow them, they will become sort of potato chip shape. They'll have negative Gaussian curvature. And so, yeah, so you can see as you grow it, it begins to have negative Gaussian curvature, and if you grow it even more, you end up with a tube. And for really, really thin disks, you get these double helical structures. So there's a central fluid core, and you have very tightly wound helices. So you can get this entire arrangement just from one system, but I'm going to focus on these helicoidal structures. Okay, so this is again that simulation I showed you at the beginning, and so this is the very beginning of the cluster that's going to form the structure, and what you can see is that it's fluctuating back and forth pretty quickly. And so we can plot the pitch length, we can fit this to a helicoid and plot the pitch length as a function of the number of threads in this bundle. And what you find is that for under about 10 threads, the probability for having positive and negative pitch, so left hand or right hand, is fairly equal. And then at some point, about I guess 10 or 12, it's going to pick a handedness and grow from there. And from this, you can see that the pitch length grows just a tiny bit, but mostly saturates. And these here are plots that show, from the point of view of every ellipsoid, where the most likely place to find a disk is. So this is the lowest energy 6 million disks, and you can sorry, no, this is time step 6 million. Excuse me for that. And as the time steps go on and the chirality emerges, you find that there is a clear tilt to these, so that the spheres are more likely to sit here and here. So that's going to give you the notion that local arrangement is going to be the source of chirality, and it could equally well have been in the opposite orientation. Okay, so this is again that same plot, but going out. I think this is every sphere in the entire simulation put one on top of each other, rather than just the nearest ones. Or every sphere in the aggregate. And so if you look at this layer of spheres, so this is a fluid layer, but if you look really closely, you find that it is a bit corrugated, that there are some ridges to it. And it turns out if you look at those, they form stripes. And those stripes are going to be the little indents where each of the layers of disks sit. So what you're going to see is that if you track, if you fit each of these threads to a helix, what you find is that you get this sort of bilayer structure of helices. And if you look closely just at this point, you'll find out that each of the helices is on the front layer is offset by a constant angle from the back layer. And so that's telling you that these live on two helicoids or helicoid-like surfaces. And they are offset from a central helicoid by a constant amount. Okay. So I guess I'm going to skip this in interest of time. But it turns out that we can play some tricks with them. We can sort of add multiple seeds of these to the simulations, and you get longer helicoidal bits. You can add multiple seeds, and sometimes they stack together. So this one is fake, but it turns out that this one will self-assemble on its own. And to do that, so this is what happens, is that you get a tiny little group of about 6 of them, and it's like a little baby helicoid riding on the mother helicoid's back. And from there, the baby helicoid has a sort of safe templated place to grow, and it's going to get bigger and bigger, and then eventually you end up with a completed bilayer structure. And so this is completely self-assembled. There are no seeds that are put into the system. So it turns out that this is a really hierarchical assembly process. So it has to go through 3 steps in order to reach this structure. So you have to start out with disks and spheres, and those are going to order in little pairs. The disks are going to stick to the spheres. Then the disks are going to find each other and stack into little threads. Then all of those threads have to find each other and assemble into a bilayer. And then once you have a bilayer, you get this ribbon that has multiple bilayers. Okay, so in the last couple of minutes, I'm just going to tell you, this is maybe in answer to, I forget who asked about the lattice of these. So this is the helical nanofilament phase. This is a phase of bent core liquid crystals, and you form these really nice arrays of nested helical bundles. So we wanted to see if we could simulate this phase as well. So the idea to do this is to take basically the same system, but add a hotspot to either side. So now this would, instead of form a bilayer, want to form a string of these. And so this is the little nucleus that is, I guess it's not a nucleus. This is a little initial aggregate. And I will fast forward. So this is still 1, it's just periodic boundary conditions, so you'll have to, this is not centered on its center of mass, so eventually it'll end up here as 1 bundle, and this is what it looks like towards the end of the simulation. So the idea here is that, again, these are nested helical layers, and each of them has a constant angular offset from its neighbor. And so this is another structure where we do get very large aggregates with a single handedness from a set of achiral constituents. And I guess this is the last thing. This is an open question. This is another image from the original paper on the helical nanofilament phase. And what this is showing is that is that you have these huge regions of homochirality. So I think the thing I didn't mention is the width of each of those bundles is about 20 nanometers, the half pitch length is about 100 nanometers, and this scale bar is, I think, 100 microns. So you have these massive, massive, massive homochiral regions coming from these very, very tiny chiral constituents. So I think this is possibly one of the cases where something like a long-range elasticity is something that is responsible for this set of homochiral structures. But this is an open question, and something that we could try to understand from these simulations is what happens when you have two oppositely handed regions coming together to form structures. So these are a couple of models of possible sets of helicoids that get joined together. Right, so these are my conclusions. I will leave that up. And thank you so much for your attention.